Okay, so after spending quite a while talking about stratospheric chemistry and ozone depletion, we now need to move down in altitude into the troposphere and talk now about reactions that occur in the atmosphere just at ground level. And particularly, we'll spend quite a bit of time talking about ground level air pollution. Now, before we do, there's one more thing we have to clarify or discuss, and that is just one more concentration unit when we're talking specifically about air pollutants. So in addition to the molecules per cubic centimeter unit and the ppm or ppb or ppt unit that we have used and become familiar with, there's also a micrograms per cubic meter unit, and this is used for either particulate matter or just for pollutant gases. And one thing that we need to keep in mind is, depending on what unit we've measured it in, we may need to know the molar mass. Now, if we're only talking about particulate matter, we may not need to know the molar mass. But if we wanted to do conversions between this unit and our other units, we would need to know the molar mass of the species in question. Now, I just want to do a couple quick examples of conversions between this unit and some of the other ones, and then we can move on into some of the other chemistry here in the troposphere. So a couple quick examples. First, say we wanted to go from parts per billion to this unit of micrograms per cubic meter. And in this case, we've specified we're looking at SO2, or sulfur dioxide gas, at 21 degrees Celsius and 1 atmosphere air pressure. So the approach is actually identical to the approach we used previously when doing unit conversions here. We simply take a look at the numerator and the denominator, and then we look at the units for that setup, and then we look at the units that we're trying to get to and just note what needs to change. So here I've got 5.0 parts per billion. So that's 5 molecules per 1 billion molecules of air. And I'm going to a numerator of micrograms per cubic meter. So in this case, both the numerator and the denominator need to change. We need to go from molecules to micrograms. So I have to convert from molecules to grams, and then molecules to moles, then moles to grams, and grams to micrograms. And then in the denominator, I need to go from molecules to a volume unit, cubic meters. So we'll take each of those individually and then simply plug them into their appropriate places. So for the numerator, I simply take the number of molecules and convert that from molecules to moles using Avogadro's number. From moles, I can get to grams using the molar mass. So that will get me to grams. And then now that I'm in a mass unit, I can go from grams to micrograms simply using the metric conversion here. There's 1 million micrograms in a gram. Set all of that up in order to cancel out my units here. And I apologize, is 6.022 times 10 to the 23rd should be molecules, not moles. And that will cancel then and result with 5.32 times 10 to the minus 16 micrograms of SO2. So we've got an extraordinarily small mass unit here. In the denominator, however, we're going from a number of molecules to a volume unit. So here, first I have to convert to moles, and then I need to use the ideal gas law to convert from moles to volume. And then, of course, I'll have to convert the volume from liters to the appropriate volume unit here, cubic meters. So I've got 1 billion molecules. I can convert that to moles using Avogadro's number. That gets me 1.66 times 10 to the minus 15 moles. Then with the ideal gas law rearranged to solve for volume, I simply substitute in the number of moles, the gas constant, the temperature converted to Kelvin, and the pressure, and I come out with 4.01 times 10 to the minus 14 liters. So an extraordinarily small amount there. But I'm not done. I need to convert from liters to cubic meters. Now, I could probably look up a direct conversion between liters and cubic meters, but I don't know it off the top of my head. So what I do instead is go from liters to milliliters, because I do know conversion between milliliters and cubic centimeters. And so that will get me from kind of a metric unit for volume to another unit for volume, but using kind of the length by width by height. So it's more about a length measurement cubed in there. And then I can go from cubic centimeters to cubic meters. So 4.01 times 10 to the minus 14th liters multiplied by 1,000 milliliters per liter. That cancels out liters. Then I know that 1 milliliter is equal to 1 cubic centimeter, so that cancels out milliliters. And then I just know that 1 cubic centimeter must be going to 1 meter cubed would be over there's 100 centimeters per meter. And so if it's cubic meters or cubic centimeters, then it'd be 100 cubed. And I cancel out my cubic centimeters and end up with now 4.01 times 10 to the minus 17th cubic meters. To complete this problem now, I have converted the numerator to the appropriate unit, the denominator to the appropriate unit. Simply substitute those into their appropriate places, make the division, and I come out now with there being 13.3 micrograms of SO2 for every cubic meter. And that's essentially a quick conversion between parts per billion or the PVX scale to micrograms per cubic meter. Let's take another example though, and say we were already at micrograms per cubic meter and we wanted to go to molecules per cubic centimeter. The conversion isn't very difficult here. The process is exactly the same. So I need to go from micrograms on top to molecules. So I'm essentially just doing the reverse of what I did in the numerator before. And then I need to go from cubic meters to cubic centimeters. That's actually a very easy conversion there. So numerator, micrograms to molecules. Well, I have to go from micrograms to grams, and grams to moles using the molar mass, and then moles to molecules using Avogadro's number. I plug all of that in, micrograms to moles, micrograms to grams, grams to moles using the molar mass, moles to molecules using Avogadro's number, and I come out with 8.09 times 10 to the 18th molecules. And then meters cubed to cubic centimeters, that's really a very simple conversion. I come out with there being essentially 1 million cubic centimeters per cubic meter. I have the numerator and I have the denominator. I essentially just plug those values in and I come out with there being 8.09 times 10 to the 12th molecules per cubic centimeter. So this is how we use this new unit for air pollutants, but essentially a new concentration unit.